Can you hear us online? Okay, well, I hope so, because the audio seems to be working. Let's see. Um, oh, I got something in chat. Yep, they can hear us. Great. Okay, we'll just wait. Actually, we can probably get started soon. Want me to get started and then just
Yeah, and then just switch off.
yeah.
Yeah.
When I get tired of talking.
Okay, yeah.
Um,
Feel free whenever you get started. Stop like
okay.
tired of
So
talking.
if I say something wrong, please correct me. Because also, yeah, it's also free. If I say something wrong, correct me. It's a test. Okay, so let's get started. So how this is going to work is we're just going to go over a bunch of the topics that we like talked about during the semester about web. And for each of these, or for some of these, there'll be quizzes at the end that we'll go over together. So I'm going to go through the slides and present things. But if you would rather just do the quizzes, I mean, the slides are available online. You can get them, so you can also focus on that. Um, Yeah, interrupt me if you have any questions, if stuff is unclear, or also if you feel like I'm going too slow on anything, just tell me I can speed up. I want to make sure it's tailored to everybody's speed here. So, web basics. So the very first part of web is how do we access information on the web, right? So how do we address things? And that's through URLs. So the way it works is that this is a identifier for a specific piece of information on the web. It's broken down into different pieces. So here on the screen, you can see the protocol, which is typically HTTP or HTTPS, your domain, port, your path, and then after the path, information about the query, so like parameters and things like this. Now, yeah, this describes everything the server needs to be able to get. HTTP, HTTPS are the most common ones, but you'll see sometimes FTP, file if you're opening something local. I've never seen git plus SSH in a URL, but it is possible. So yeah, the domain is essentially pointing to what website you're looking at, so it's pointing to like the right server. Um, so this actually points to a specific IP. It's just you use DNS to retrieve the IP. Um, I don't know. I don't think we're going to talk about DNS in this recording. I think I'm recording. Yeah. Yeah. There's a little thing here.
Okay, cool.
Wait, I'm not sure now. Am I recording?
Can go
It's
to
this little thing here. So
yeah, I think you're good. Yeah, yeah,
okay, yeah, we're recording. Okay. So yeah, so the domain, it points to a specific IP. This is done through DNS. So basically a DNS server is it's a service that converts a like human readable domain name to an IP. The port, which is just which network port you're using. So typically for HTTPS, it's usually 443, and that's the default one. So in this case, we could just drop this part and it would be the same URL. For HTTP, it's 80. Okay. And then the path, so that's on the same server, just where your thing is. So like if you remember project 3, different parts of the website were at different paths. And then this goes into like the query information. So this is for GET requests. This is optional. Typically when you load a web page, you don't have any of the query part or the fragment part. But the query part is just going to contain parameters that might be used. So for instance, um, if you were to do a GET request, it would just be put here. And then the fragment just points to the specific part of the web page you're looking at. So which header you're looking at. Okay. Any questions about URLs? We'll talk about them again. I mean, at this point it's kind of abstract, but like when we talk about say margin policy and things like this. Now, the way we communicate with the web, the way we retrieve this information that's specified by a path is through HTTP. There are more modern protocols like HTTPS or Quick, but essentially they all build upon HTTP, which is the most common protocol used to communicate over the web. And it's a request response model. So your client requests information, fetches a page, or sends information, and then gets a response saying whether the thing was successful or if it was not successful. Um, so yeah, HTTP 1.1, which is like typically what we refer to when we say HTTP is text-based. So that's something you can actually see, like it says get HTTP something. But then there are more modern versions like 2 that are byte encoded. Quick uses this, for instance. And then if you layer encryption on top of it, which yeah, it's not said here, it's just going to be hidden, but it's the same thing under encryption. So the structure for a request, and this is the same basically across the board, is that you specify first what method you're using, the path, so that's the path part of the URL, and then the protocol version. Now, what really matters here is method and path. Protocol version is not very useful here, but this is just to say what you're doing, right? So different methods that exist for get, post, there's like put, delete, but those are more rarely used. Essentially, get is supposed to just get something from the server, as the name says, and isn't supposed to make any changes. So it's just going to pull something. Versus post is going to change something on the server side. So it's going to have some impact. So for instance, if you're just going to like retrieve a web page, you're going to use get. But if you want to, for instance, log in, you're going to do a post. It's going to send your password. Or like if you just want to like change some sort of state. The difference is that you can actually have parameters in both. So get and post support parameters. Get, the parameters are just going to be put in the URL directly, like we saw earlier. For post, you can actually directly pass it some data. And there's different ways to encode it, but essentially the data is part of the HTTP itself and not in the path. Do you get the difference between both get and post? And the other ones we don't really care about too much, but they fall in one of these categories, either like data part of the thing or data in the actual URL. So now that we've covered how you access a page, so how do you like retrieve it and then what protocol, you get a page back, which is typically used like written in something like a mixture of HTML, CSS, and JavaScript. And this is basically can encode any web page, any application. And it's always so like it's always this sort of back and forth, like the client makes a request, gets the response back, and this response tells the client what it needs to get extra. So you'll get a first thing, then you'll get like that'll tell you, okay, you need to get these other resources, et cetera, until you've filled out all the information you need. Um, and this is a process until like the user takes an action. At that point, it's going to trigger a whole other set of requests. So the kind of like the backbone of all of the web is HTML. So that's the main language used to describe the content of a web page. This at this point is like has no formatting. It's just a way to say here are the elements on the page. It's built with tags, so it looks a little bit like XML, which is another sort of like nestable tag language. Each tag says what the field represents. So for instance, if it's a link, pictures, scripts, things like this, and then the actual part inside the tag is the text that's associated with it. Now you can think about this as some sort of just different types of headers, right? If you were to like write a web like a Word document, you'll have like large headers, smaller headers, main body. The same system here. Tags like H1, for instance, to the main header, H2 to H6 are smaller headers. P is for paragraph. Um, we don't really need to know most of this for the class, I think, but it's just interesting for like if you ever want to go into like the actual web page and figure out what's going on, it's nice to know a little bit about the tags to be able to like just parse it. One thing I'll mention because it'll be relevant later, frames are a specific type of tag, which loads another whole page into the first page. So it's just saying within these tags, I'm going to have some other web page. This is useful for isolation, so you can make sure that anything inside of the smaller frame can't touch anything outside the frame. And is used typically for payment websites sometimes, like you'll have a separate frame with a payment and things like this. Now, HTML by itself is ugly. It's going to look just like a bunch of text on a page. So we can style it using CSS. And CSS is just basically a bunch of directives saying how you want to style the different parts of your web page. So like the color, size, positioning, and essentially CSS is very powerful. You can make like, I don't know if it's Turing complete, but like you can make a lot of things with CSS and you can make things look good. CSS is also super annoying to write. And in my experience, length models are not very good at doing it. But this is what brings you from like 90s websites that were horrendous to today's websites, or let's say websites maybe 10 years ago that have really just CSS. These days you have like more complicated things on top. And JavaScript is kind of the programming language of all this. HTML, CSS is mostly static. It's just directions on how to display the page. JavaScript tells you how to execute actions on the page. So like how to have things move, how to have things that are dynamic, where if you click on a button, something happens. It basically just runs script in your browser on the web page. Knowing JavaScript is not in scope, but you've used it in the past for projects to do different types of attacks. And some of the things we've used and are interesting to know are these directives here. So window.location encodes the location of your current web page. For context, there's sort of true attributes in JavaScript that represents your current document, the DOM, and you can access it through these directives. Document cookie returns all the cookies, and then the fetch directive is this function is going to go get some URL, which can be useful, for instance, in cross-site scripting to be able to get somebody to execute something on your behalf. Okay, any questions on the basic web stuff?
So for the CSS and HTML, we just need to know it's kind of a basic description, not like each component what it does.
Yeah, you just need to know like the basics. So for HTML, when we say not fully in scope, that is kind of vague. You should be able to know like what the very basic tags are. Like for instance, A is a link. I mean, these things here, like a script tag, a iframe tag. Don't need to know like the like specifics of how you actually set attributes of what each tag actually means, just like very basic things. For the other ones here, not in scope for CSS for sure. For JavaScript, not in scope. But it's probably important just to know what these things here mean, but nothing else really.
Be familiar with syntax, especially if you used it during project 3. Usually in an exam setting, we're pretty lenient on syntax, but we should still be able to like know what you're trying to do if like the exploit includes any of those tags. And if we think it hasn't been brought up a lot in like project 3 or something, then we'll put it in the reference sheet.
Okay, and then is that everything we've gone over? Yep. Any other questions online, maybe? Okay, we can move on then. You want to take over foreign policy?
I can talk about same origin policy. So
There.
okay, nice. So same origin policy basically deals with the question of like if you have a with GitHub and then a tab open of like Gmail, like what prevents them to be able to write information from read information from each other's website, because that would be kind of insecure. And the answer to this is same origin policy. So how we define an origin is given the URL, the origin is going to be the protocol, domain, and the port. If like the port is not specified, the defaults are 80 for HTTP and then 443 for HTTPS. And so basically if like both of them don't have ports, you can assume that they are the same. So it's just important to be able to identify when different URLs have the same origin. Okay, so I'll go through some examples of which ones are the same origin and which ones are not. Yeah, I'll give you like 10 seconds to like think about it. Okay, so for the first pair, they are going to be the same origin. You can notice that like they only differ from the like /A and like /B, but since these are the path, then we don't care about them when determining the origin of the URL. And then for the next one, these aren't the same origin because the one on the right has a different domain. It has the www, whereas the other one doesn't. Okay, and then this next one. Also, they're not the same origin because if you look closely, they have different protocol. And then lastly, this last one's also not going to have the same origin because they have different ports. Is this clear to everyone why these are or aren't the same origin? Cool. And then some exceptions to same origin policy. Whenever we have JavaScript run on a page, the origin of like what we say like the JavaScript code will have the origin of the page that loads it. So this is really important because this is something that we can take advantage of in some attacks. Because usually, like if we were to say that this code has the origin of somewhere else, it would be really insecure to like run it. But actually, how same origin policy works is even if we have this like script tag and the source of the code actually comes from somewhere else, as long as it was loaded on a specific page, that page will identify it as having the same origin as it. Images have the origin of the pages that they came from. So this is like kind of the opposite of JavaScript. Even though the page like loads an image, even if the like source attribute comes from a different origin, then we say that it has a different origin between where the image came from and where it loaded. And then finally, if we have a frame embedded on a page, we say that the origin of the URL is the URL where the frame is retrieved from. So for example, if let's say we have a page, we load up GitHub, and then inside GitHub, there's a frame of Gmail, then we say that GitHub can't read any of the contents of the Gmail frame. The opposite should also be true, right? The Gmail frame should also not be able to read any information from the GitHub like page.
And same for the images. Because an image could potentially contain some code or something, it can't interact with the environment around it.
Yeah. Okay, cool. Any questions on these exceptions? Okay. That was kind of short.
I can take over if you want. Let's see.
Okay.
Okay, so cookies now. So cookies are a way to save information with the browser. This is a way for you not to have to log in every time you go to a web page. Otherwise, like every time you close the browser and open it again, you'd have to reconnect. And it just allows websites to store information about you. Now, when people freak out about cookies, it's because it also allows to store your ID so that like advertisers can track you across websites. That's another topic. So cookies are stored basically as name value pairs. So it's just some sort of like variable name with a variable value. But they have other attributes that tell you how you can use them and where you can use them. So the first attribute is domain. That's the domain that set the cookie. So for instance, calcentral.berkeley.edu, any cookie they set will be associated with that domain. The path is the path on that website where the cookie was set. And there's now a couple other more like security features. The first is HTTP only, which says whether to allow JavaScript to access the cookie. So typically you want to enable this. Otherwise, it means that a script could read the cookie and then potentially do something with it. Secure is whether to send the cookie only on HTTPS or not. Also, again, a security feature. If you have a cookie that has a sensitive value, you probably only want to send it over HTTPS to avoid it being leaked. Same site is the policy of how the cookie is attached to requests. So what happens in browsers is that when you do a request to a website, cookies that match the domain and path, and there's specific rules for this, will automatically be attached to the request. The problem with this is that you can abuse this to do attacks. So same site is just the level of policy and the sensitivity you want to associate with this cookie. So when strict is enabled, it only attaches cookies where when the site making the request that like actually is meaning the request the same as the site that set the cookie. If you have a more strict, so strict instead of lax, we'll also check for the refer. So check that the origin of the request as well. And the expiration is just when it should be removed. So typically, Session level things want to have an expiration date, but maybe longer things don't want one. Typically when you say I want my to want to be logged in for a whole week, it'll just set the expiration on the cookie for a whole week. Now, the way that cookies are set is that you want to ask the browser to set the cookie rate. So the URL must end with the cookie's domain attribute. And so you want to make sure that the domains match up. You can't just do .com, otherwise this cookie would be set for every single website. But you can do the level above. So for instance, berkeley.com works. And then you can set path as much as lax as you want. Now the interesting thing here is, did we say this somewhere? Let me just. We don't. Great. Okay, so something that we're not actually saying here, but it's interesting. Cookies can span like different domains. So for instance, it's not exactly clear here, but like let's say like I have a cookie for berkeley.edu. And correct me if I'm wrong here because I'm going off script, but if you have a cookie for berkeley.edu, that's set for berkeley.edu, it'll also be sent to calcentral.berkeley.edu, or it can.
There's a question.
Sorry?
I think there's a question.
Okay, there's a question on it. Well, okay, so I might have spoiled the question, but anyway, these rules allow you to do some interesting things, and that's why you don't want to have cookies for .com or .net. Otherwise, that means that every website with .com will have your cookie sent to it. And that can be an issue because then like potentially you can be leaking information to the wrong websites, right? Also could be a vector for denial of service if you put a bunch of cookies on .com and then it then gets sent to every single website. So yeah, we'll go into this in more detail with the question, but essentially this is an interesting distinction between how cookies are handled and how same origin policies is handled. There's slight differences. And I think these like lead to interesting corner cases of like policies for browsers. Anyway, going back to the script now. So one use of cookies is for session management. So the way this works is that when you log in, and this is typically different from how we did it in Project 2, but it's a kind of a standard way to do it online. When you first log in, you are giving a session cookie. So like once you've logged in, you've proven you're the right person, it gives you a unique session cookie that you have to store. And now every time you make a request to the website, you're going to show this cookie. You're going to show the session cookie. So the website knows who you are and you don't have to re-authenticate. And the problem with this, and this is something that you've probably explored in Project 3, is that if you can get a hold of somebody else's session cookie or something similar to it, through SQL injections and things like this, you can now usurp their identity and pretend like you're them. Because the only thing proving that you are who you claim you are is this cookie. So how does this work? Well, when you log in, there's a random number that's generated that's saved in a local database on the server and returned back to you. And now when you come back later and you show the session cookie, it just goes to the database and says, hey, well, this already exists, so I don't need to re-authenticate the person. So this is how you persist through different connections. Any questions on this or the cookies before? Yeah.
Right, so what if like there's you already used the cookies and then the next time you try to go into the web server, someone else is trying to act as you, like spoofing, like how does it work again?
So let's say you log in, right? And a session cookie gets created and it's just like, and there's this happen, right? When somebody else comes back with the session cookie, it doesn't matter if it's you or somebody else, as long as the session cookie is correct, it'll just authenticate you as the right person, which is where you can hijack this, right? Now, and that's actually an interesting question. Based on that fact, what would you set this attribute to be secure for this one? So like for session cookies, like you want to prevent this being leaked, right? So if you don't want it to be leaked, should you allow this to be sent over HTTP? No, right? Otherwise, somebody could like look at like just record your network activity and like learn your cookie. Should it be accessible from JavaScript? I mean, it doesn't mean if it's accessible, it's going to be breakable, but in theory, in general, you want to avoid having it be accessed by anything except what really requires it. And that's the last thing. What you want to set for your expiration? Do you want to let it never expire, or do you want to have an expiration date on it? And think about like when you're logging into websites, can you log in just once and then never logging again? Yeah, eventually like you have to re-log in, which is a security measure because you want to make sure that there has to be some freshness, right? Otherwise, like if it lasts forever, then yeah, eventually somebody can break into your computer and steal it. Um, so yeah, like it's using cookies requires careful design to really always think like, what's the least privilege I need with this cookie to make sure I don't leak it, I don't leak information. Okay, do you want to take over for this one?
Okay, sure. So what actually happens when GitHub loads? So you can kind of see.
Wait, I think, I'm sorry, there's a question.
Okay.
Um, when would you want to set it should be to be true versus false use cases? Um, well, so in general, if you're only using HTTPS, you want it to be always set to sorry, it's not secure, it's this JavaScript one. Use cases. So in general, you want it to be false, just like principle of least privilege, right? Like if you don't need it. But you might have some cases in which a website requires further functioning to be able to access cookies. Like for instance, I believe some of the CAPTCHA or like that system, the way that works, I think, don't quote me on this, is that there is some client-side JavaScript that's obfuscated that runs basically some check to prove that you're human. And so then it saves some sort of cookie or like access some sort of cookie to be able to like from some sort of secret generate something else. The reason why it does this is that if you want to on these websites that have this, if you want to do a request, you have to attach a specific cookie that proves that you're human, and that cookie is going to be generated, like the value is going to be generated from a JavaScript script that's running locally. And this proves that you had to run that JavaScript to be able to get this request. The idea is that if you by doing that, it prevents people from directly accessing the network API. And actually, it has interesting implications in like today's world with like web agents and LLMs because that means you can't directly access the web page without having an actual browser that simulates it. So that's one case where you want to be able to have JavaScript influence the value of the cookie because you're using that as a proof of humanity mechanism. I can't think of another use case right now, but we can think about it and get back to you.
Okay, cool. So I'll continue on anatomy of request. And the section's mostly going to talk about like, we already talked about how we set cookies, what a cookie looks like, and maybe what we want to use cookies for. But this section will talk more about like what actually happens when we attach cookies and when should the browser, when should the server have the cookie attached to the request. So an example of this is like when we load GitHub, there's like a lot of functionalities. You can see your repositories, trending repositories, and recent activity. Yeah, and like JavaScript all when the page is loaded. Oh. And this basically happens because we're making a bunch of like API requests. Your laptop is opening GitHub, so it makes like a call to GitHub server. You get like a response back, which is all the stuff you see on your screen. And then after that, you can continue interacting with GitHub's website. And this will also make other API calls, as we were talking about earlier, like GET requests or like POST requests. Yeah, and so some of these calls will need cookies attached to them in order to work. And basically, what you should, something that's very important to know is what are the requirements for cookies to be attached to these calls? Because these cookies are being stored on the browser, but it's the server that will need this information, right? So the requirements are that the URL domain must end in the cookies domain, and the URL path must begin with the cookie path. So a way to visualize this, I don't think we have it on the slide, is like the cookie domain and path should at least be contained by the URL, like either as a sandwich or they're like one-to-one or something like that. So in this case, based on the URL that we're requesting, the URL domain is github.com, and then the path is dashboard/recent activity. And so what will happen is we'll look at like all of the cookies that are stored in the browser. And for each cookie, we'll look at both the domain and the path of the actual cookie. And then if the requirements that we said before get fulfilled, then we'll attach it to the API request. So in this case, remember that our URL is like github.com and then like /dashboard recent activity. And then since the domain and the path is since the URL domain is ending in the cookies domain, which is github.com, and then the URL path is starting with the cookie path, which is like just /, then this cookie will get attached to the request. And then yeah, the screenshot just shows that we can verify that in the request header we can see the cookies. Okay, does anyone have any questions on that? Yeah, step by step what just happened?
I just want to clarify something that I
Yeah.
said that is wrong. So CAPTCHA is not a good example of this because CAPTCHA, I just looked it up, doesn't use cookies. It could, I mean, it could have been a design, but they just use all like other piece of information. An example of using HTTP only set to false is preferences. So like if you want to save the fact that like you like your website in English versus French, or you want to save the fact that you like want your color to be like dark mode instead of you need this information to be saved so that the website can just like your JavaScript can just like be able to like act on it, right?
Yeah.
If the JavaScript wasn't able to read this, they wouldn't be able to change the website link for things like this.
So that's why it doesn't need to be sent over HTTPS.
So HTTP only is not for HTTPS. That's the one that says whether or not JavaScript has access to the cookies value.
Okay,
Oh yeah, sorry for interrupting. I just want to make sure that the CAPTCHA thing is not it doesn't have cookies, and I said something that was completely wrong.
Okay, we can keep going. So yeah, the next question is what happens if CS161.org or like any random website makes a request to github.com while a user is currently signed into github.com, right? So the nuance here is that because they're already signed into github.com, there's most likely already been a session token or like cookie already associated with the user. So then they're authorized to make requests on GitHub. Yeah. So that gets into cross-site request forgery.
Okay. So actually in this case, we're gonna talk. This is gonna go back to the HTTP only thing. So the way cross-site request forgery works is, say CS161 wants some information from GitHub. Now it can't directly like same origin policy, it just can't directly like access GitHub. Like let's say it's under the tab, access that tab because the web browser won't let it. But if the page made a request to github.com, let's say, I mean, any request, under the standard policy, what would happen is that the browser would see this request, would attach all the cookies that are required, so any cookie that's associated with GitHub. And that means that if the user was signed into GitHub, it'll perform this request like if the user made it. Meaning the source website, CS161, is going to be able to get information back that only the user should be able to know. So this means they can steal information and the user would never know about this. So this is cross-site request forgery. Why cross-site? Because it's one site attacking another site, getting information from another site, and request forgery because it's creating a request that looks like a user one, so the browser actually attaches all the cookies to it. So this is a problem because, say, I include this HTML in a web page. It's going to try to, the browser is going to see this, say, okay, I want to load this image from the bank. It loads this URL of the bank for the bank. If cookies didn't exist, that'd be fine because, well, this would not do anything given you're not logged in. But when the image is loaded, the browser is going to attach all the cookies for the bank set previously, including the session cookie. And so the bank will think it's a legitimate request and then actually execute this. Now, this is all due to the cookie policy, right? If the cookie policy was a little bit different, you would not associate any cookies with this. and thus you wouldn't be able to actually execute these attacks. So the first defense to do this is for the target website, so like the website that's like the bank website, to add a token. And this token is just a way to prove that the request came from a web page generated by the bank account. So the idea here is when you load the bank web page and you want to do a transfer, somewhere hidden in the web page is going to be a little token. And this token is going to be some random value like this. And the server is going to say, I'll only execute any requests you make if you include this token. Now, if you're using the bank through its regular website, the token will be associated and everything will go smoothly. But if you make the request like here, because you're just making this directly, it's not going to attach the token to it because it just doesn't know what the token is, and so the request will fail. So this is kind of like a site, like a target site defense. The site says, okay, use tokens like this to defend. Did I just explain this? Okay. So the way this works in practice is it's saved in the unlike a session token, which is something associated with your username and password that's like spans the whole login session. A CSRF token is generated each time the page is loaded. So like every new time HTML is gonna have a new session token. And so it's sort of a one-time code just to make sure you freshly access the web page that can do the action you want to do. Does this make sense for this first defense? Can you think of an attack against this?
What? I don't know. Since it's saved in the HTML itself, I don't know.
So, for instance, if the web page that is doing the attack loaded the whole HTML for a bank,
Yeah.
could they extract the token and then do the request again? No,
No.
because of the same origin policy, right? If it loads the entire page into like a frame, it can't actually access the inside of it, right? I mean, if same origin policy is done well. Now, there's another way to do this, but it's more involved through cross-site scripting. And this is where HTTP only comes into play again. Now, this is more like for, it's kind of advanced, not necessarily super important, but like I think it's an interesting reason why you want to use HTTP only. So CSRF tokens, or session tokens for that matter, are stored cookies, right? I mean, they can be stored cookies, not necessarily CSR, but like one implementation can do that. And what you can do is that you could have a script that runs on the other bank account. So you inject a script that would read the value of that session cookie and then save it, or the CSRF token if it's stored as a cookie, and then save it somewhere else. So this isolation here, having JavaScript not be able to read cookies, is a way to prevent that too. Now, I mean, that's not a very practical attack. It's way more involved. So in general, CSR tokens are a very safe way to do this. I hope I didn't confuse you more by trying to give a convoluted example, but did this make sense in general? Why this would work? Like this token?
The CSRF is considered with the HTML itself, and the session is considered with the cookie itself.
Yeah, so I mean, you can think CSRF is going to be a new one every web page, but it is provided. I mean, there's different ways you can actually implement it. One way is to just have it part of a form. So say you have a form to do a transfer, a bank transfer. You can have a secret part of the form, it's just a secret field that contains the token, and it'll be associated. You could also do it as a cookie if you wanted to. You could have it be like a one-time cookie, like a short-lived one, and overwrite it. Implementation-wise, there's a different way to do it, but the main idea is just to say every new page load will have a new token, just to make sure that you're not, and you can't reuse it. Once it's been used, it's done. Cool. Okay, so the second defense is a little bit different. So the second defense is saying you You also can have the server check if the request came from the right spot. The problem earlier was, go back to the example, when you're doing this, the request is being made by cs161.org, but it's being made to another website. And so what you can do is you can just specify an origin header and refer header. What this means is the origin is where the website that made the request, and the refer is a specific web page that made the request. And the server can have a policy saying, well, if the origin or the refer doesn't correspond to where it's supposed to be, I just reject the request. So in this case, if we did the form from earlier with bank, okay, there's no example. The origin would say, well, cs161.org, and then the bank website would say, hey, well, this is not my URL, so I'm going to drop this. This makes sense? Yeah.
Kind of what's stopping the origin, like just spoofing that, like you saying it actually did that.
So that's a good question. So the origin and refer are set by the browser, right? The browser itself sets this. Now, one possible attack, I don't know if this would work or not, but if you find a way to convince the browser a different page, you could maybe circumvent this, but I don't think there's a way to do that. Yeah, I mean, unless there's a bug in the actual browser, which, spoiler alert, a lot of exploits, even today, come from bugs and implementations of browsers where some of these things are not perfect. Actually fun to look at CWEs and look at like how many browser versions are broken. And when you get a Chrome update being like, oh, you have to update right now, that's usually because they found a big bug that means people can circumvent some of this stuff. But in theory, you can't circumvent this. It's like the origin is just going to be whatever the website you're on is, right? Now, a third defense is same-site cookie flags. This is a little bit different. The two others were server-side defenses, right? The server was checking if the origin was correct. The server was checking if the token was correct. Same site is the server telling the browser itself when to send the cookie. And so this is just saying, okay, when I specify a new cookie, I'll tell you like same site none, for instance, just always attach the cookie to this request. But if it's some other value like strict or lax, it tells the server to only send, sorry, the browser to only send the cookie when the request is being made by the actual website. So this is different because this is now saying the browser itself will just never associate the cookie with it, instead of having the server actually do the filtration and saying, okay, I'm going to drop this request or not. So the difference between strict and lax is not said here. I believe the difference is in the origin versus refer. So if we went back here, the origin is the website, like just the domain that sent the thing. The refer is a specific page. I think strict is going to check that the refer is the right one. So basically you made the request not only from the right domain, but also from the right web page. If you do lax, you're just saying, I just want to make sure the origin is the correct one. So what happens in the bank account example? Well, CS161 reaches out to bank.com. The browser looks at the cookie. If the cookie has same site equals lax or strict, it says, hey, well, this is being sent by a different origin than the cookie's origin, so I'm not going to attach it. Does this make sense?
When you set it to lax, you said it's set to the current site or current?
So think about lax and strict as being similar. It's just saying don't attach the cookie if it's not being made by the right website. I think the difference, and I'll double check this, is that strict will make sure it's the right refer. So like you're actually sending it from the right page within the website, whereas I think lax is just checking that it's the right website itself. And so in the example, the refer and the origin are both the CS161 website. I think it's just the different, like, basically like origin is the actual domain, the refer is the actual web is the actual page, which I'll double check. I can actually figure out what like it is in our example. Where is it here? So with all these defenses, it seems like CSRF is no longer an issue. Well, the problem is that this depends heavily on server and browser implementations, right? The problem is browse same site is a pretty recent flag. When I learned about this a while ago, it was really not implemented anywhere basically, except for like Firefox. So you can't always trust the browser will do the right thing. So you always want to use one of the first two defenses, either the token or the refer/origin verification. And the other problem is that for checking that, sometimes some networks for efficiency might drop some of the non-essential fields. And so you might actually lose information, which means you don't know what the origin was. So you want to basically implement as many of these defenses as possible to make sure you're doing something safe. Okay, any questions before we go to the exercises here? And also I will double check what the difference between strict and lax is just to confirm this. And yeah. Okay, let's get started. So Q3, I don't know why it starts at 3, but Q3.
Okay,
You
yeah,
want to take over?
yeah, I can go for it. Okay, so I guess I'll just give you guys a minute to think about this. Yeah.
Also, when are you guys going to be recording?
We'll do it as soon as possible. But yes. Okay. Okay, cool. So for this question in same origin policy, which of the following are used in determining the origin? So if you remember all the way at the beginning of the presentation, we talked about the definition of the origin, and that's what you'll use for this question. So remember, it's the protocol, domain name, and port. We don't care about the IP or the path. Okay, next question. I'll give you guys another minute to look at these questions. Okay, cool. So for this question, it's really important to, if we go back to the code that they're using, is the script with origin of like the API that the third-party API that they're using. And so going back to the question 3.2, there's a concern that they can use this library, or it's insecure if the library is compromised. And so is this a valid concern? Yes, because if you remember the exceptions to same origin policy, even though the source code of the JavaScript is from this third party, because it's being loaded on the Bear Bank's webpage, then it will have the same origin as the Bear Bank webpage. Okay, and then the next question, 3.3, they decide to move it, the form to like an iframe. And then they're saying, okay, now is like this still insecure? And it's no, because from the same like slide with the exceptions, if you now have it embedded in an iframe, then we shouldn't have it that they can, the iframe and the page can't communicate or like read information from each other. Did these questions make sense? Yeah.
You explain the question?
Oh, yeah, sorry. Okay. So, yeah, I think I skipped over a little bit on the code that's being run. So basically the premise of this, like question is that they have like some login code, that they're using this third-party service, this A/B testers, and like something important to know is like the script where like the source code is coming from the third party application, right? But we said that all the way in the beginning that whenever like even if we have JavaScript on the Bear Banks website, um, and the source of the actual JavaScript comes from somewhere else, because it's being loaded on the Bear Banks website, then the origin of it will automatically be like the Bear Banks website. So because of this, we kind of don't check for what kind of information is being read from the actual source code, like what that information has access to, because we're running it from like loading it in from our website. We say that it has the same origin, and so we give it a lot more freedom on what it can do. And so that's why it is a concern. Did that make more sense?
When you said it's the same site origin?
Yeah, yeah, they'll have the same origin. Even though the like source code is from a different one, because of how the exceptions to same origin policy, it will load in as having the same origin. Okay, cool. I'll give you guys another minute. Okay, cool. So this question has to do with when we send a request to a server, what cookies will get attached. And okay, so for this question, it'll only be H. And this has to do with like the requirements for cookies getting attached. If you remember, the domain of the URL should end in the domain of the cookie. So that eliminates I. And then the URL of the URL path should start with the path of the cookie. So that eliminates G. And then for H, even though it has that secure flag, it doesn't really impact us here. Any questions for this one? I'll give you guys another minute. Okay, I'll go over this question now. So this question kind of just goes over the different protections that we talked about or defenses against CSRF. So we said that you can add CSRF token, to the transfer form, and this is one defense. And another one is adding a refer header on the request so that we know where the request is coming from. Moving the transfer form to an iframe doesn't really do much for CSRF attacks since or like you more so talk about that with same origin policy, but it doesn't change anything about the cookies that are being attached and things like that. Okay. I'll give you guys some time for this one. Okay, so we have some questions in chat. One of the questions is like, I think in the example where we had like the bank website, and then 161 was making a request to the bank website, what would be the origin, what would be the refer.
Make sure it's good. Turn off.
Yeah. The bank website would be the origin and 161 would be the refer, right? The refer is where the request is coming from.
So in the example, is it that which example is that the one
161 was making a request to the bank website from
both are, so the difference in refer and origin is just the level of verbosity. So basically both refer to the last URL visited before the request was made. So in the case where it was CS161 that was making a request for bank, the origin was CS161.org, and the refer was CS161.org/ wherever we were on that website. So in the example we had later with Piazza, for instance, the screenshot, the origin was piazza.com, and the actual refer was piazza.com/ like whatever, I forget what the URL was. The difference that you only need the origin for all these policies, but the refer itself is useful for more like for analytics, to just be able to track like which web page referred and like did this actual request. But they both refer to the web page that made the request, not the web page where the request is being made.
Yeah, and then another question is like, when would you want to move like a piece of code or into like an iframe? And this more so has to do with like if you have different parts of the actual website that you don't want transferring information from each other. Whereas this is a bit different, like CSRF is a bit different because it's specifically taking advantage of your cookies rather than which is browser side versus like the information that's being stored server side. Okay, cool. I think I gave you guys a good amount of time to do this, to do 3.6. Okay. First of all, can anyone tell me what an on-path attacker is or like what they're able to do?
They can listen in on the communication on the packets, and they can also modify, I think.
Not modify, but they can spoof packets. So,
So spoofing means adding packets?
yeah. Yeah, so basically the whole point of like what Eve can do here is that they will be able to see the request as it's going through. So because of that, within the request, we'll have the session token as well as the contents of the transaction. So they'll be able to learn that. But they won't be able to learn the password because that won't be attached within the request. They'll also be able to repeat Evan bot's transaction because they saw the whole request and they can just send it again. Okay. So I'll give you guys some time for this question. Yeah, I think it's the same. It's a similar question just with encryption now. Okay, since this question is pretty similar to the last one, I'll just keep going. But the difference this time is that they can't learn the session token or the transaction because the request is encrypted. However, they can still repeat the transaction because they can just resend what they were able to see and it'll still look just like the first transaction. So it'll go through. Oh yeah, and specifically it's because they're using Elgamal, which is vulnerable to replay attacks. Okay. I'll give you guys some time for this one. Okay, so for this question, it's both going into security principles and a little bit of networking. Yeah, basically the problem with why the previous scheme was vulnerable is because they used Elgamal and they tried to come up with their own encryption scheme. So instead they could have just used TLS, which is known for end-to-end safe encryption. And the lesson here is to not build your own crypto. Okay, that's the last.
Okay, before I go to cross-site scripting, I have an answer on what the difference between blacks and strict is, which is not what I was saying. So strict is what we were saying, right? It's you don't attach a cookie to a request if it comes from a different origin than the one that set the cookie. So if CS161 wants to call bank.com, it's not gonna have any cookies with it. The problem with this is that there's a user experience problem. Say I send you an email with a link to Facebook and you click on it. If the content, if the cookie policy was strict, then when you get to facebook.com, you're not going to be logged in because it's not going to have it's not going to attach the cookie with it, right? The annoying thing with that is like that means if you store a web link anywhere else, or even like if you're on Google, right? You're on Google, you click on the link to get to the web page, you would never be logged in, so you'd have to log in every single time unless you actually typed the URL yourself into the browser. So that's where Lax comes in. Lax will do the same as strict, except it will attach the cookie in some specific cases, like top level pages. So if you're doing a get to the top level of a browser of a website, so for instance, bang.com slash or bang.com slash index, or like some of these top level pages, it will attach the cookie to it. And so it won't attach it if you're doing post requests, if you're with iframes and a couple other things. So basically the difference is just that it does attach the cookie in some cases, which makes the user experience better, but doesn't really damage security too much. I don't know of any attacks against the fact that Slack instead of strict, unless your website is so poorly implemented that just the fact you're loading the web page, the first page, is a security risk in itself. I mean, this is not in scope for for the thing, but just I figured I wanted to clarify what the difference between is. For what it's worth for you, just remember, same site, none, it means cookies always associated. Same site, lax or strict means it's only associated if it comes from the rain domain. And this detail about lax, where it does associate the cookie in some cases, I mean, it's interesting, I think, for like learning about what these things mean, but not really relevant for like the class. Okay. So cross-site scripting. So this leverages what we talked about earlier, which is that if you execute JavaScript on a web page, it's going to run with the context of that web page, even if the JavaScript was written by somebody else. So if I load an untrusted library, it's going to run anyway with my own policy, my own origin. So if I'm on evil.com and I run some JavaScript, it's only going to be able to run with the origin of evil.com, so it won't be able to see the contents or modify the contents of github.com. But if I find a way to get the JavaScript to run inside of github.com, then effectively has the same user privileges as anything running on github.com. So why is this an issue? Well, because it can now do a bunch of stuff like run requests from the context of GitHub. So this bypasses all of CSRF because like if there's a token to be associated, or it'll be associated. If there's some sort of like same origin policy, sort of same site policies, it'll be associated with it too. You can steal cookies if they don't have the HTTP only request. You can do a lot of things, right? So one standard way of thinking about this is usually only possible if the website has some sort of like security vulnerability. If I enter a query here, what you see is that the query is just going to be a parameter of the GET request here, right? So it's just going to have it be up there. Now, in this case, because there's no sanitization, if instead we put a script, it's going to actually execute the script. And this is a typical example of how you can actually perform an XSS attack in practice, which is if you find a web page that has this vulnerability where it's not sanitizing its input somewhere, you can replace the regular input by some script. And now that script will be run in the context of that website if you load the website. So specifically, like in this case, what we did, we attacked ourselves, right? We just put a script in our own browser and like, great, we have an alert locally, but who cares? But if I just send a victim this same link with the actual the queries that are in here, the problem is that now if they click on this link, it's going to execute that from their perspective. And because there's no sanitization, it's going to actually execute the script. There are different ways to do this. This is just one of them. You could also have some stored XSS where the script is stored on like some sort of database, and then same problem, not sanitized. So when the user goes to get it, it executes in their context.
Like, what do you mean script is stored on a database? Like, is the script JavaScript? So how would JavaScript be stored in the database?
So essentially, the reason XSS mostly happens is when something that's not a script is treated as a script, right?
Mm.
So here, something that's supposed to be just a variable, a search variable, is treated is executed as a script.
Yeah.
And this is because when you're rendering your HTML, if you don't do anything specific, you're just going to put the content of the variable in the HTML, right?
Yeah.
And now if that is a script tag, it's just going to execute as a script, right? And in the example here, the way we did it is we said, if I specify this parameter, the square parameter, and it's a script, it gets into the backend. The backend populates the HTML with this variable, doesn't sanitize, sends the HTML back, and now when I execute the HTML, it's going to execute the script. But other ways to do this would be, say, there's some stored variable, like there's some database like in Project 3, or there's some file list of files or things like this. If one of those things is not sanitized, it's kind of the same thing, right? If the website puts this variable into your HTML, it's then going to be executed when the person renders the HTML. Yeah.
Wait, what do you mean by sanitization? So for this,
so sanitization means that in this case, like if I enter this directly, this actual value, like script alert one scripts, this is going to be saved as is in the query. So it's going to be passed to the server as is. And then it's going to be pasted directly into the HTML of the page. And the problem is that And this is a very typical thing in like, there's a lot of attacks around this, in SQL and XSS, and also like more recently, like prompt injection attacks against language models have the same problem. It's your rendering engine, your thing interpreting your content, whether it's a web page or a SQL thing or your LM in more recent context, can't tell the difference between what is just text and what is a control sequence. Now, these script tags here are control sequences, right? These are things that tell the HTML or tell your browser, I'm going to execute what's inside. But you pass them to the actual browser as pure text. And in practice, what you would like to do is to say, okay, well, because this is all text, none of this is an actual control sequence, so none of it is executed. And that's essentially what sensation is doing, is it's making sure that any input you provide is going to be treated as text and not as a control sequence. And we'll see later in SQL, it's kind of the same idea. Stuff you pass, it's supposed to be a variable, is treated as a control. And to link to more recent stuff, prompt injection attacks against language models abuse the fact that the language model doesn't know what's text and what's instruction. And so you can convince the model to do something it's not supposed to do by saying, hey, this is actually not text, this is actually your instruction, you're supposed to do this instead. And it's the same exact problem. It's that there's no clear way to separate instructions from the data. Now, for language models, it's still a very open area of research that we haven't figured out how to solve yet. Even though David worked on this and
David Mack.
yeah, we wrote a couple papers a couple years ago on how to defend against this. And so anyway, sorry, this person, but like it's the same fundamental problem as this problem of like separating instructions and data, right? So that's what XSS is. I mean, what is Stu2? Sorry. Okay, so stored is what I was just talking about before. This is an example of it. You write this tweet, it gets stored in Twitter's database. Twitter doesn't actually sanitize it. And then when it renders it on everybody else's web pages, I mean, not in this specific case because this is a joke, but it renders it, the web page thinks it's a script. Now, in this case, it's not happening, right? Because like it's actually displaying script, so that means it was sanitized.
Yeah.
And thankfully, Twitter today is not just, I mean, well, I don't think so. It's like you can't actually do this attack. So yeah, on this tweet deck thing, apparently it's possible to do one. So what are the defenses? Well, the main thing I talked about was sanitization, right? It was saying you make sure text is treated like text in HTML. And how do you do this? Well, you replace every specific symbol that HTML sees. You replace it with a other character like this, like NLT or NRT, which just says this has to look like a chevron, but it's not an actual chevron, so it's not going to execute as a script. The problem is that this is very complicated because you can think of a lot of edge cases where it could fail, especially on more complicated things in HTML. And so there are standard libraries that do this. And to my knowledge, it's still an open area of research where there are still like solving this perfectly is not necessarily always easy. Another way to do this is through the content security policy, where the website tells the browser which resources a specific site is allowed to load. And this says basically you can only load scripts that come from a specific URL, so don't execute any scripts that come from anywhere else. Don't run any scripts in line. That means don't run any scripts that are like specifically tags. They have to be loaded from somewhere else. Disable some dangerous API calls. So basically, this is just sandboxing your execution in some way and saying you can only trust sources from some things. So, for instance, your content security policy could say only allow to look like execute JavaScript that comes from /script.sh, like some sort of endpoint. And now if I do my attack again, well, even though it sees it's script, it says, well, yeah, this is a script, but it's come from a parameter. It doesn't come from this page, so I'm not going to execute it. Yeah, this doesn't work in CSRF because CSRF it triggers a whole other like vulnerability. Because CSP deals with what the client is able to load, not the server, what the server can run. Do these make sense? There's kind of another way to think about this instead of just sanitization is you can have what we call prepared queries for SQL, and like you can think about similar things for HTML, which is you have a first pass where the HTML is rendered, and then you put the content in later. And the idea is like if you load the content later and it's already rendered, it's not you can't actually execute the script. Which is not really that useful for HTML. I mean, I think there are some like what's it called? Some libraries that kind of do this, but mostly for XSS, you want to just do sanitization. Content security policy is a little bit more complicated. I think like it's hard to set this correctly because you have to really figure out exactly where you want your scripts to come from. So more specifically, it looks like this. Basically, like your content security policy has this basically list of sources of where it's posted. So I have to do things. So like for instance, here it says connect source self, uploads, and blah 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 stuff. This is a list of all the places where it can actually run the scripts from. Okay. Do you want me to do this or you want to take care of the problems?
Sure, I can do.
Okay. Any questions on the content before we move to the exercises? Yeah.
So for the content security policy, is it mostly based on like APIs or is it the way that it's showed in the feature?
So this is something that the website will give in their response headers as a specific header. It's just the server saying this is what you're allowed to use and not allowed to use.
Oh, so the server says.
So the server says this, right? The server says, hey, you can only execute scripts that come from these specific places, right?
Oh.
And so, for instance, like a way to do this is like a lot of the times, if you're writing HTML correctly, or not correctly, sorry, in a production environment, you won't actually have any inline JavaScript. You'll have just a script that's called at the end, being like, "Hey, load this specific page," and that's the script you want to run. And then your content security policy would say only use that script, meaning if there's any inline any inline JavaScript that gets added to your thing later through an attack. The browser would just say, well, this is not part of the website I'm supposed to be using for this. It's not on the /script endpoint, and so I'm not going to listen to it.
Like, are you talking about like script, like say script people, script.js, like that stuff?
Yeah, script. You put a script. You put a tag saying script source equals script.js instead of just putting a script tag and then directly putting your raw script there.
Oh. Yeah, this mostly seems just like URLs.
Yeah, these are mostly just URLs of like where the scripts are about to be coming from. Mainly this is to say like if somehow somebody injects a script saying like, oh, go get a script from their website, it won't let you do it. I mean, there are probably more complexities of content security policy, as you can see, like there's a bunch of keywords here. No need to know exactly what they mean. Honestly, I don't know what they all mean. But it's just like different levels of the policy.
Okay, cool. So now do some questions that have to do with CSRF and excess attacks. So I'll give you some time for this. Do people want more time for this question or can we go over it? Because I know it's a bit longer. Okay, let's go over it then. Okay, so basically for this question, you'll basically construct a stored XSS attack. Mallory will post either like an image or a script that looks like that. There's multiple ways you can do this on the forum so that when the TA loads it in, the request that she wants to execute to change her score will run. Yeah, there's multiple solutions for this, but an important note is you can't just put a link on the forum that will make the request that you want, because in this question, you want to assume that they won't click on the link, they'll only load the web page. Yeah. But for like the image, for example, it'll automatically make that request because it has to try to fetch the image. Okay. Moving on. So now in this question, there's a CSRF defense is enabled. Okay, I'll go over this question now. Okay. So the question basically asks like, oh, when Mallory changes her attack URL from the link on the forum to this link, like what defense did she probably circumvent? And it's going to be refer checking. I think the main tip off for this is that she was able to change the like URL to come from instead of the like web forum. Now you can use the redirect to make it seem like it came from within the CS161.org website. Yeah. And then like you could also do this question from process of elimination. Like a lot of these aren't even CSRF defenses. And with the CSRF tokens, since that is something that you would yeah, I think we talked about how it's kind of hard to circumvent that. So that this wouldn't be a case where you're able to circumvent CSRF tokens. Okay, any questions on this one? Yes.
I'm confused between the different arguments for so like because when you go to this new website, like it'll go to that and then it'll automatically redirect. So that changes to the refer, but why doesn't that change the origin?
Do you think you can speak more on that?
I feel like it should. Honestly, yeah, I mean, I'm seeing this honestly, but I'll look into it right now, but
Yeah, we'll have to get back to you on that.
for me, origin and for me, this should have been both, not just refer, because in my understanding, the origin is just the like domain that did the thing. Refer is the actual web page. And so when you click on this link through the redirect, you've like rewritten the last thing that did it. And the last thing I did was like 161.org/log. And the origin of that is 161.org. So there might be something that we missed, or that I missed about origin staying to always be this, like doesn't make a lot of sense, right? Like, how do you determine then what the origin, how many steps back have to go, right? So, I'll check this right now. But I still stand by what I said, I think, until I can prove myself wrong. Origin should just, the origin here should be CS161.org. So I'll check, but I think these two could have been valid responses, but I will check right now. Okay.
In the meantime, we can move on to the next question. Okay, I'll go over this question now. So, the main observation that we want to make for this question is that when Mallory visited the URL, where she had the argument be some script, when she visited that URL, the script that she injected, actually ran. And so, she was able to see that the website is susceptible to reflected XSS, and that whatever we put within the script tags, will be run. So based on this, we can try to get the session token of the TA. Okay, so this is the answer. Yeah, as we said before, like we'll try to be pretty lenient on syntax. So for this question, as long as it shows that you wanted to run some script at the vulnerable URL, and then you make a request to Mallory using some method, and then within this request, it does something such that it'll send the TA's cookie to it, then that's good enough for this answer. Something to show that kind of logic.
So I found out about the for immersion thing. It's a corner case that I don't even know why they asked that question, but they did at some point. In the case where there's a redirect, and only in the case where there's a redirect, it is possible for the origin that refer to not point to the same domain. So in this case, because you're clicking on this page from the web form, right? And it redirects, it gets to this page, but then that redirects you to this page, right? In this case only, the refer is going to be the last thing in the chain, which is this page, but the origin is still going to be the thing that initiated the original action, which was clicking on that link, which is the web form. That's the only case in which you can have an origin, and I mean, as far as I know, I could figure out, it's the only case in which you have an origin and refer that are just not pointing to the same domain, is when you have this redirection. And so I think the way you can think about it is like, think about what the last user action was. The last user action was clicking on this link. The redirection was an automatic thing. So the refer is going to point to the last thing in the chain of actions, versus the origin is going to point to the last thing that the user did. And the origin points to the domain versus the refer points to the web page. I honestly would be surprised if that's something that, like,
Yeah.
like it's a very minute detail. Yeah, I don't think. I mean, if you are, don't sue me. But I really don't think it'll be tested on something like this because like it's a corner case and. But it's a reason why. I think refer checking used to be more common in the past. Like that was a more common thing to do, like maybe 10, 15 years ago. We've moved more to origin because it's a more reliable signal of where the person actually was. Yeah. Any questions about that? Yeah.
When you say redirect, it redirects to the initial website and then it takes you to the one that's updated, right? After you update the.
Yeah, so the original link on the web form was this, right? And so what happens that like you do one action, you click on this, but there's two actions happening behind the scenes, which is the first action is goes to this login page, has to all the cookies or whatever you want. Oh no, it doesn't because security policy. But then it redirects you to this page. And so the second action, if you're only doing refer checking, the second action is going to look at what the refer was, and the refer was this page, and this page is the right page, so like it's going to attach the cookies. But the origin is the origin of the whole action, and the origin of the whole action is the web form. So you don't associate the cookies if you were checking origin as not refer. But again, this is a corner case with redirects that I don't think you're expected to know about. I mean, if you haven't heard about this at all before, it's probably because it's unexpected. And I didn't know about this myself. I mean, I that's why I was surprised that like origin, it wasn't both origin and refer checking.
Okay, cool. And then was there any questions for 2.3? Okay, on Zoom, they asked, how do we construct this URL for 2.3? I'm not sure if they're asking about like thought process on how to do it, but how I would think about it is, yeah, once we know that we can construct any script, and it will run, when we visit the link, how I would think about it is in order to, log in as the TA, we probably want their session token. This is probably something similar that we've done for project 3. And then how do we leak it? The problem says that Mallory has their own website that we can kind of construct ourselves like what we would want it to do, right? So the idea is, I know this is like a lot of syntax that we said you probably don't need to know, but the main idea is that what do we want to do? We want to run some action on Mallory's website that will leak the cookie. So how we can do this is we can make a request to the website where the argument is a cookie, and then we don't really care what this graph.cgi endpoint actually is. Like, I don't think they said I don't think we showed you what that endpoint actually does. You can define that yourself as long as you make it clear that you're trying to visit, you're trying to make a request to Mallory's website with the cookie as an argument so that Mallory can do whatever she wants with it. Yeah, and then it's also important that you don't simply just put the URL to Mallory's website. For this, you need to also give some other syntax that will make sure that the request is actually run.
Okay, SQL injection. So kind of similar to what we were talking about earlier, SQL injection is an abuse of the execution engine inability to distinguish between instructions and data. So SQL is a query language, it's called structured query language, which is used to query databases. Sort of standardized way of querying databases. We're saying like what fields you want to get, what conditions, so like what are the conditions on them and where you want to get them from. So this is saying like give me the fields from this table that have this condition. For instance, get me the username of from like the username from the user table where the password equals something, which you should not be doing this in practice, like, but you shouldn't be storing passwords in clear, but anyway. Other fields that you've probably used in Project 3, Union, where you can combine multiple queries that have the same number of columns and column data types. So basically, say you have 2 tables and you want queries that are unrelated but over both that return the same columns, you can do union. And then drop is most are from a security context because drop is the way to remove a table from the database. So if you're able to call drop, you're able to delete a whole database, right? Now the problem we're hinting at here is kind of the same thing with like distinguishing instructions from data, is to say you can inject code if there is a variable that's supposed to be text that's treated as code somewhere. And the way this happens is if you have an eval, for instance, on Python, or there's also the similar thing in JS, any variable that's passed to that eval is going to be treated as code. And the problem is that this can be dangerous. Let's say in this example of a calculator, if I give it input that's a valid input, it's just going to work. But if I give it an input that's something else, it's going to run this thing as an actual command. And this is a problem because now you're executing code when you just didn't want to, right? SQL injections are very similar. It's gonna say, say I have a query to this, like this is a typical way paradigm for doing SQL queries is that you have some parameters in the get, and then you're gonna select the username from users where the username is this and password is this. This is just saying like, please get my user, right? But the problem here is that as you can see, these things here shouldn't be treated as text. They should just be treated as arguments. But if I just copy and paste the value here into there, I can actually get them to be treated as something else. So if the username is garbage or 1 equals 1, with this is the common sign in SQL, what happens is that this gets pasted into the SQL query, and there's no way for the actual SQL engine to know the difference between what was the instruction, so what was the actual format string, and what the data part is. And so when it sees it, it's going to execute and say like, hey, well, this is the end of this part here, and then it's just going to do these, right? See this as an instruction, right?
Like, is it just gonna skip the and password and just comment that out totally?
Exactly. Yeah.
Okay, sounds good.
And so it executes this thing. And so the problem here is that it means that if you're not doing any specific defenses, which any guess at what defense you could use here, like that's similar to something we talked about before? Yeah, sanitization or other things like prepared queries. If you're not doing any of this, it's always possible. I mean, it's going to be possible for you to convince the backend basically that like your data is actually not just data, but it's actually like a statement, like the or the 1 equals 1. So how do you mitigate it? Well, the first is escaping inputs, which is basically sanitization. It's just saying you're going to take the input that's a text and just replace anything that could be interpreted as a SQL keyword, and you escape it out. This is just a way to say like, okay, you can't close your quotes, you can't add comment, you can't add any of this. This is, again, very tricky to write yourself because depending on the actual SQL library you're using, there could be very complicated escape queries and things like this. So you want to make sure you use a standard library to do this. But the better way to avoid SQL injection is parameterized SQL or pair statements. And this is something different where you compile the query. So each query is some sort of language, right? And it's going to compile into some sort of program. The program is going to be what it's actually going to be running. So like running on the database, right? So I mean, I'm not sure exactly how that works depending on the database, but it's in sense the set instruction is going to be running. If you compile it first and then you pass the user inputs as inputs to this program, now these things will be interpreted directly as like text and will never be seen as instructions. And it's kind of like similar to what we were saying before, right? If I mean, eval doesn't let you do this, but like, let's say I replace eval by something else. If you pre-compile the program, now whatever you pass is going to be just a string, and it will never be seen as anything else in the string. So that's kind of the idea here. Okay. How many do we have? Oh, I don't want to set solutions. You want to do you this, or you want me to do it?
Sure. I think it'll be pretty fast.
Okay. Sorry, I talk a lot, so we might be a little
Yeah.
bit of time, but I think we'll be done on time.
Yeah, okay. Yeah, we have one practice problem left where we're going to perform some SQL injection. Yeah, so for this question, we have we're implementing we have a website that implements two-factor authentication. So how it works is they have this table of users, and then there's a username with the code, and then whenever a user wants to log in, they'll make a post request with their username and password. Assuming that the password is correct, the server will randomly generate a 10-digit numerical code and then store it in this table. The server will then set a cookie with the name of to FA, and the value should be the user's username in the user's browser. And then the server also sends a text to the user's phone with the code.
So does this, since I just wanted to interject once.
Yeah.
So in point 3, it says user's username in the user's browser. So does this indicate that people can have the same user can have multiple usernames or something like one on the user's browser, one on the server? Like why are we specifying user's browser? Just wondering.
I think they were just being explicit.
Okay, explicit,
because
okay.
of it's a cookie, but yeah,
Okay.
cookies are always stored on the browser.
Oh, sounds good.
Okay, so after the text is sent, the user makes the GET request to confirm the code. Okay, and then the server runs an SQL query where it queries this table for that code, and where the code is submitted by the user. And then we'll check that the value of the SQL query matches the username in the cookie. So now we'll get to the actual question. So now we want to construct an input for code that would cause the SQL query in step 5 to return Evan bot. Is the first part. So I'll give you guys a minute to think about it, but the question was, what can we submit? Because in step 5, the code is submitted by the user such that the SQL query will return F input. So
I just had a question. I have a question. So
yeah.
Oh, never mind. They're getting sent code. Okay. I'm sorry about that. I thought they were not getting sent. Sorry.
Oh, and another important clarification at the bottom that I didn't say out loud is that you can assume the user has an entry in the table. Okay, I'll go over the answer unless anyone else. Okay, so basically we'll perform some standard SQL injection. So the original query was up until like this code equals quote. And what we can do is we can prematurely end this quote. This will return nothing. Or like this will make it so that this is like never true, but then we'll also do or username equals Evanbot. And so that will return Evanbot. And then in order to take care of like the mismatching quote that was like in the original query, we will comment it out with two dashes. Okay. Any questions on this one?
What does
Yes.
the last dash do again? Okay.
Oh yeah. So in the original query, what's gonna happen is it's gonna do select username from users word code equals and then like the variable that we're replacing code with inside two quotes, right? But in our answer, we part of our attack is adding one quote at the beginning in order to like end the original query. But because of that, now the quote that was like originally in the SQL query, like the other one that was matching with this one, is still there.
Yeah.
So if we didn't have any dashes here, then yeah, then we would get a syntax error because now we have an unmatched quotation mark. I guess technically, like sometimes what people can do is instead of having two dashes, you simply don't have a quote. You enter your answer here,
Yeah.
like after Evanbot, but usually it's safer to put the comments in case there's like more to the query, even more than the quotation mark, that you don't know is there. Yeah.
I don't know. I was doing my answer might be wrong, but I did like quote semicolon and then I put select username from users or username is equal to Evanbot and semicolon and then comments. So like it's basically two queries.
Okay, that works. Wait.
Like
I'm not sure.
basically I'm having the first query as it is, except code is going to be single, like just an empty string. And then I'm putting a semicolon after that. And then I'm entering in select username from users where username is equal to Evanbot semicolon comment.
Yeah, I'm not sure why it says there's a answer because I'm
possible. It's like there could be many.
So the problem with
Oh,
yours
yeah.
is that you're
yeah.
doing two select operations.
Yeah.
But if you do two select operations, usually SQL will like it expects only one operation. So you want to use a union instead.
But I was doing a semicolon. So like I had select semicolon and then select number, so that would still.
So the things that like a lot of times, semicolon colons are going to be filtered out. Even if it's not like so, if you look at project 3, for instance, like you can't actually include one, like it'll be filtered out.
Oh yeah.
Through like some mechanisms, and also if you have two selects one after the other, I'm not exactly sure what the behavior is expected to be because like you're executing two instructions, so it should return the last one, but it's not entirely clear. It's a little bit more deterministic if you put a union.
Yeah.
So you just union the two selects.
I actually think, I think the one in lecture uses a semicolon. So I think if you did it on a test, you would still get credit.
Like what I said.
Yeah, I think if you use a semicolon or a union. But yeah, like we said, like in project 3, like the semicolons were filtered out. So if you want to give like the simplest answer, like the safest answer possible that you're sure like will succeed, it would be this. Okay, I'll move on. Oh, sorry, that's the answer. Okay. How can you log in as Evanbot without knowing their password? And you can use payload as a reference. Yeah. Okay, I think we're out of time, so I will just go over this answer. But basically, the key insight that we can use here is that in step 6, all they do is make sure that the SQL query, like the output of it, matches whatever is in the 2FA cookie. So using our last SQL, like previous answer, we know we can change the SQL query output in a way that it will return Evanbot. So now all we need to do is change the 2FA cookie to Evanbot. And now when the GET request is ran, it will see that they are both equals to Evanbot, so then it will log in as Evanbot. Yeah. Then there's a couple more questions. So due to time, we'll just go through. Okay, so what are some defenses that we can use against this? Yeah.
I think A.
Yeah. So A is going to be actually the only answer. Rate limiting doesn't make too much sense since we're only making one request. Putting the hash of the username instead of the cookie. This also doesn't work because, as we said before, we're exploiting the fact that we don't actually care what the value of like the SQL query output and the 2FA cookie are as long as they're equal. So if we can just ourselves calculate that hash, we can still make them equal by inputting them in like the same way. And then using a 20-digit code instead of 10-digit code, again, doesn't really do much because we're injecting the SQL in a way that we don't care what the original code was. Yeah, I'm not sure why the solution talks about firewall. Yeah, I think that's a typo. Okay, last question. So in this question, basically they modify the scheme to enforce that the code has to be exactly 10 numerical digits. And they're asking if this will also be a good defense against our SQL injection attack. And this, the answer will be true. Yeah, it'll be impossible for us to inject SQL if we can only input digits. Okay, I know we went through the last parts really quickly. Does anyone have any questions? This is the last part of the review session. Okay, cool.
Cool, thanks. I'll stop the recording so it can start processing. Stop recording.